Okay, can you quickly do audio and video check real quick?
Sure. Audio okay?
Yeah, audio is okay.
All right. And I put video on and
All
I'll
right,
share.
we can see you as well, so that's fantastic.
All right. Okay. And hopefully you can see my screen there.
Yes, we can see your screen. Right now you have Teams desktop client.
Mm-hmm.
So we see your deck, but oh yeah, perfect. We see your deck in the presentation mode. So you're good to go. So since it's 12 p.m. Eastern time, just go for it. Thank you.
Okay, sure. So my name is Dave Wenzel, and I'm still trying to figure out how to get dual screen monitor to work. If you have any questions, just jump in and ask them. Uh, and I guess Prashant, you're going to monitor the chat as well, so that's fine. Okay, so this is building a neural network from scratch. There's my contact information, and I actually have a Git repo that you can pull this down for. So this is actually a workshop I do, and it's a lot of fun whenever we do it. So I thought I would give you the Git repo, and maybe if you want to, you can do this stuff on your own. It takes about 6 hours to do it, but it's a lot of fun. So I'll give you a little background. What we do in the workshop is I took some of the graphics from the AdventureWorks stuff that Microsoft has, and I kind of hacked up a situation where we have these graphics and we want to create a neural network to say basically what product are they. So it's actually camping supplies. So we look at what the product is, and we see if we can build a neural network, again, totally from scratch, that can actually do the prediction of this camping gear. What you'll find is that you can do it, but it's very hard, and your accuracy is not that good. And then at the end, we say, okay, that's kind of cool and everything, but nobody really does neural networks from scratch unless you're a PhD student. So what people normally do when they build neural networks is they find a neural network out on the internet that does what is really close to what they want to do, and then they do something called transfer learning. And we'll discuss what transfer learning is, but basically what it is we say we want to maintain the architecture of the network, but we want to take off the last layer where we're doing the predictions, and we want to say, I don't want to predict camping gear, or I'm sorry, we don't want to predict whatever it is it was predicting when we pulled the model off the internet. Instead, we want it to predict camping gear. And you'll find immediately that the accuracy is really, really good. And then we go over how to just kind of take it the last mile. It's a lot of fun. You do not need to know a lot of Python or any of that stuff. You kind of learn it through the process. So if you want, you can download that if that's something that's interesting for you. If you're not a data scientist, it's really fun to kind of see how this math works in the background. And if you are a data scientist, it kind of gives you a feel for how transfer learning works, if you're going to go and do this stuff on your own. So that's what we're doing. Again, it's a little workshop, but for this hour, I'd just go over essentially what a neural network is and a little bit on that stuff. So we'll kind of jump in here. I need to. Okay, here we go. So I think I already covered what we're gonna, cover here. But again, we'll do the lab on your own if you want. And again, you have my contact information. Feel free to contact me if you run into any issues. So we're gonna just understand what neural networks are. I think the next presenter then is taking this to the next level and is doing TensorFlow, which is kind of the implementation that we kind of do within the lab as well. But by all means, it's not the only one you can use. It's helpful to understand. I see people all the time. I'm a stickler for terms, and words have meaning. So what is the difference between artificial intelligence, machine learning, and deep learning? So artificial intelligence is actually nothing new. It came out before the 1950s. There were papers written on it, and it's going to go over everything that we're going to go over for the next hour, what artificial intelligence is. The problem is it never really took off, and it died in the mid 80s there, and it died because really the compute power wasn't there to do this at scale. So when they came up with the algorithms for artificial intelligence and neural networks, conceptually it worked, and it worked on small data sets, but and we just didn't have the compute power. So artificial intelligence kind of died out, and what took over was machine learning. And we'll go over machine learning in a little bit more detail in the next few minutes. But essentially, machine learning, if you want to think of it as the most easy way to think about it, is it's just linear regression. That's the absolute simple way to look at it. We'll go into a little more detail, but it's essentially just math. And this kind of took over, especially with the advent of tools like Excel that can kind of do the linear regression right in the tool for you. And that's kind of been going on until around like 2010 or so, when deep learning took over. And deep learning is kind of artificial intelligence reborn. And essentially, deep learning is convolutional neural networks, or just neural networks in general. There's other types other than convolutional. And essentially what we're doing here, it's the math that we're going to cover. And the math is actually ridiculously easy once you see it. Some of the concepts are a little weird until you see them in practice, which is, again, why we kind of do the lab, so that you can see, that's what the math is doing under the covers. So these are the three things. And generally, when you speak of these things, everybody just uses the term AI, artificial intelligence, to refer to all of it. But machine learning is kind of a subset, and then deep learning is a subset of artificial intelligence as well. So that's what that is. There's another way to look at this too, and I usually just whiteboard this. So if you can see my whiteboard, I'll show you this. And this is more for application developers than anything else. When you think about like traditional programming, so this is a traditional application, and my drawing skills are terrible, but this is a typical application that we've probably all developed for years. Basically, the way applications work is there's functions, right? And the function is the code you write. And then when you write the code, then you're expecting the user to give input that exercises the function. So the functions receive a series of inputs. And then coming out of this kind of black box, although it's not a black box because you have the source code, is the answer. So if you want to think of it this way, if you're building like an e-commerce website, if you're building Amazon, or even if you're building like Windows Calculator, it's very simple and it follows this paradigm. I have a function, which is my code. I have a series of inputs I'm going to get from the user, and out the other end spits an answer, essentially. But what we're talking about with machine learning, so I use the term machine learning, but overall it's just artificial intelligence, or AI is a better way to look at it. It kind of works like this. It works in reverse. So this is the code, and what we're going to do is give it a series of answers into the code, and we're going to give it a series of inputs later, and out of that we're going to derive a function. All right, so we do it in reverse. So think of it this way. I want to predict whether or not a bank loan is going to charge off. That's my machine learning algorithm. So I have the answers, if you think about that. So the answer is, I have the loan ID, I have all of the statistics around the loan, how much was it for, debt to income ratio of the borrower, all those things, and then I know its final disposition, which is the answer. Loan charged off, loan did not charge off, right? And then I have the inputs, which is what the user is going to send in later, that we're going to do the prediction off of. The answers, essentially, this is our training data here, right? And we're going to send that training data in, and we're going to have the machine learning algorithm kind of churn over that, and we're hoping the other end is going to spit out the function that then we can use again as the input at a later date. So that's kind of the easy way to think about machine learning. So we're kind of flipping it on its head. We don't want to write a lot of code. We want the machine to learn the code given a series of answers that we've provided. So that's a little bit about what machine learning is. In reality, like most ML practitioners don't kind of really think of it this way. They think of it in a little more simplistic manner. They say, this is something in the middle. It's a black box. It's going to take data that goes into that something, and then we're going to shoot out the other end the model, right? So the black box is what, always concerns people, right? So that's if I build a machine learning model, is it interpretable? Is it explainable? Things like that. But really, it's a black box. Now, many algorithms, you can pull it apart and you can get the information out to see what it's doing at each step. But what you're going to see with the neural network stuff that we're doing is it's even more exacerbated, this black box concept. You can get at it, but you're really not sure what it's doing because the math it's doing is very easy, but it's doing it billions and billions of times. And in aggregate, it's really hard to figure out what's going on. But in this case, the model that comes out is really just the function. So the function is what we're going to use, or as data scientists call it, the model. And then once we have that model, we can again do predictions with new input. So that's kind of how I like to think of this stuff. So just a little side on that. So when we go through this for the next 50 minutes or so, this is going to be a problem if you've never seen a convolutional neural network. The stuff I go over, it's not going to make a lot of sense. You just have to suspend disbelief and then wait until we get through the whole thing, and then hopefully at the end it'll kind of click for you. And again, that's why we do the lab, so feel free to do those on your own. So let me pop my presentation back up here. All right. Any questions so far? Okay, cool. Let me go through here. Okay, so, and again, these presentations, by the way, they're all in that GitHub repo, so it's not like you need to take notes or anything here. So basically, when we're dealing with machine learning or AI, we're defining a function that takes inputs and generates outputs. All right, so that's the function there, and the X is the inputs. In data science terms, we call these the features that go into the model. With machine learning, the featureization is absolutely critical. So if I want to calculate loan loss, whether or not a loan, is going to charge off or not, I have to be very careful with the features because the ML models, they're a little bit brittle and they're going to need you to scrub the data, or what we call data wrangling. And it's very important to get that right. So the featureization is important. With deep learning and these neural networks, it's less important. Okay, so you want essentially the algorithm to learn the not just against the data, but to learn the patterns and what it needs to featureize. So that's one difference between a neural network and, say, a traditional ML, like regression style algorithm. So these are the features that go in, or the inputs into the function. And again, the function's the model, right? And then what we're doing is we're trying to get the answer, which is the label. The answer is the label. So when we're training data, the label is essentially the answer that we're looking for. So if you want to think of it in terms of the loan loss provision, I'm sorry, I keep saying provision, the loan loss prediction, the label would be the loan charged off or the loan did not charge off. Okay, so that's pretty easy. The example we're going to do today is a very common one. If you're a programmer, you probably know about Hello World. In the machine learning and AI space, there's basically two machine learning two Hello World models that people talk about. One is called MNIST. So I'll just write that up on here. You can research that one on your own. MNIST is basically a series of handwritten characters that you classify. So basically, if I write this, we want the machine to say that's a 0. If I write this, that's a 1. It's not a 7. So that's MNIST, very common. And this is one that we use in the workshop. If you want to do that for homework, we use the MNIST data, and then we use the MNIST data, which categorizes, zeros and ones and handwritten digits. We use that to tell if, one of our products is, a tent or, various other types of camping gear. And it always blows people's minds. Like, you're telling me I can train data on handwriting and it can predict whether something's a tent? Yeah, it can. And we'll go over why that is, again, for the next 45 minutes or so. The other common Hello World data set that people use as data scientists is called the IRIS data set. And that's what we're going to use through this one here. So the IRIS data set works something like this. There are 3 classifications of irises. I'm not going to try to pronounce those. They're up there, but we're going to call them, for our terms, 0, 1, and 2. So this is a classification problem. We want to say, if I see a picture of an iris, is it a 0, 1, or 2? Okay, so that's what we're doing. It's classification. Those are our labels. Okay, and then again, this Hello World data set called the IRIS data set, we're given a few things. And what we're given is sepal and petal measurements. So the sepal, well, I have it on the diagram there. What is the sepal and what is the petal? Those are the measurements we're given. So there's 4 measurements we're giving, and then based on those measurements, we need to predict the species. Okay, so that's the data. So we're going to do it first using that data. And then we're going to come back and we're actually going to use the images instead and see what that would look like. But conceptually, it's the same thing. It's just if I look at the image, I get a lot more information that I can use to make a prediction instead of just 4 data points here, right? So those are, by the way, the length and the width of the sepal and the petal. So going to get a lot more information from the picture, but we're also going to get a lot more noise. So we need to factor that into the situation. So again, these are the features or the X that goes into this. Okay. What's going to come out? Oh, lovely. I wrote over that. What's going to come out is essentially probabilities. So these would be the Y's. So the probabilities, in the way I have this written out here in this slide, is a vector, and it says 0, 1, 0. And what that is it's probabilities of, is it a setosa, a versicolor, or a virginica? So that's class 0, class 1, and class 2. And here it's saying, again, the way I have that, more or less saying it's a versicolor. And again, it's doing that based on these 4 numbers. So that's how this works. So give you a little lead up. This is how the algorithm, or this is the data set that we're going to plug into the algorithm. Okay. And again, the way I'm doing this here, using this data and not the image data, I'm going to do more of a classical machine learning problem. All right. So we'll start with that, and then we'll flip over to the next one. So again, what this is saying is that mostly it's probabilistically going to be a versicolor. All right, cool. But let's say we wanted to do that same problem, but we wanted it to look like a neural network. Okay, so what is a neuron, first of all? So I'm not going to get into all of the stuff in the brain, but you've got these neurons in the brains, and between the neurons there's pathways, and the way scientists think this works, I guess it's never been proven. Maybe it has. I'm not really sure. Basically, you learn, and in the process of learning over the course of your life, these neurons get well defined. All right, so here's kind of the way I like to think of it. Imagine you're a baby and you have you're new to the world and you don't understand things, and you see a lion, right? If you see a lion, you're probably going to freak out because it's bigger than you. It looks like it has sharp teeth, and that doesn't look very good. And it might be walking towards you with a scowl, and just naturally fight or flight kicks in, and lions aren't too good, right? But what happens, if you see that lion at the zoo, you're going to freak out. But then you learn quickly that, oh, there's this other thing between you and the lion called a fence. And if there's a fence in the equation, then I don't need to be quite as freaked out that this lion is going to kill me. So, maybe I don't need to, fire the neuron that says, run as fast as you can in the other direction. And then likewise, if you see a lion, but it's on the Discovery Channel on TV, you quickly learn, oh, well, there's absolutely no fear whatsoever here. So don't fire the flight neuron. So that's how kind of neurons work. Over time, as you learn a bunch of these features and you put into situational awareness, does the neuron fire? And essentially, that's what we're doing with deep learning and convolutional networks here. So what I'm displayed here is these are inputs into the neuron. So you can think of it very simply in the lion situation. The neuron is the top, or the line going into the neuron at the top. The neuron is representing the flight reaction. Okay, and the first one is I see a lion. Okay, that's bad, but I see the lion and it's on TV. So those are the 2 inputs to the neuron. So now, does the neuron fire? That's the key thing. And if the neuron fires, that's the output coming out of the other end. So again, this is what we're trying to build when we build these algorithms. What we're doing over time when we are exposed to the lion is we're learning which input should be weighted most. Okay, so if the top one is the lion on TV and the bottom one is a lion in real life, The lion in real life, I need to fire, and that one needs to be weighted more. So the thicker line indicates it's a higher weighting, and that indicates, boom, the neuron gets fired. Okay, so that's what we're attempting to learn. Going into this is, if you remember, our y equals f of x. These are two of the x's that go into the neuron firing. Obviously, there's potentially thousands or millions or billions or a large number of these inputs. This is just a simple diagram, shows two. Okay, and essentially when we activate, we need to figure out, well, okay, we have the inputs, and now we're going to figure out the weightings, which ones are most important. We're going to weight those higher, and then we're going to say, once we know all the weightings, sum them together, and then we're going to apply what's called an activation function. And the activation function says exactly what it means. Do I activate the neuron? All right, and it learns that over time, the activation function, right? And then boom, it fires if the activation threshold was fired. What we're attempting to do over time is we need to learn what these weights are, right? So there's X1, X2, they have weights, and weight 1 is much less than weight 2. So we're going to learn these weights over time by looking at examples, okay? So let's stop doing the lion example and go back to the iris example. The more irises we see, we know which parts of the iris are most indicative of their classification. And what this is saying is weight 2 is more indicative, or I'm sorry, feature X sub 2 is more indicative, so we need to weight that higher. So that's the weights going in. Again, the Y is the output, so it's the activation, the result of the activation function, rather. And our equation gets changed to this now. So before it was Y equals f of x, now it's going to be Y equals f of x comma w. So it's the features and their weights summed up and brought in together. Okay. Now, just to make things interesting, what we do in data science land when we build these neural networks is we add what's called the bias. The bias is just some number, and we just throw it in kind of randomly, but it's not a random number. It's just a made-up number, and we throw that bias in, and then we say, as we see more examples of irises, we're going to adjust that bias. So the bias adjusts the system as a whole. The weights adjust the individual features, okay? So don't get too hung up if you don't quite understand the bias thing. It's just a number we throw in that we can adjust to make the system react differently, okay? So our new function is y equals f of x with the weights and the biases, okay? So that's what we're actually looking for here. Okay, to be more specific, this is the actual function. So we're going to sum up all the weights for all of the inputs. So that's what that's saying. So all of the weights, in this case, we only have 2. We're going to sum those up, and then we're going to add in the bias, okay, which is just, again, initially, it's this random kind of number thing. Okay, and then what that is a sigmoid function, and all that says is it squashes that result down into a number that's represented between 0 and 1. That's all that's saying, right? And then we're basically saying, if you remember back at the beginning, we give probabilities to that, and then the one with the highest probability essentially gets the 1. That's the squashing function, right? Or we can actually just put the probabilities out there, and essentially the squashing function makes sure everything falls between 0 and 1. That's the easy way to think of it. So very simple math here. So let's take a look at an example not using images, but just looking at the petal and sepal lengths and widths. So remember those 4 things out of the data set. All right, what would that look like expressed as a neural network? Okay, we have 4 inputs. So the first layer of the network has 4 inputs, okay? So 4 x's, and now we need to figure out what the weights and the biases are. So what we're going to do is we're going to give a whole bunch of these values for length and width, sepal and petal. We're going to give these into our formula here, and then we're going to have it do its calculation. Now, why does it go from 4 to 3? Okay, 4 is the number of inputs we have, right? Length, width, and by sepal and petal. And the output is whether or not it's class 0, 1, or 2. So notice we're going from 4 down to 3. Okay, and that's essentially a neural network. In reality, to be very specific, This is what's called a perceptron, okay, but which is just a special type. All right, so let's look at it again in, oops, I'm going the wrong way. Let's look at it again using some data here. So assuming you've got 6.6, 3.2, 5.8, and 2.4, what happens is it goes through its formulas and it says 0.3, 0.4, and 0.3. All right, what I'm doing here is I'm saying when I run one set of values, one iris through the system, this is what it comes up with. All right, so I have a generic kind of variable random bias, and I also have random weights because it hasn't learned anything. So I just assign things at random, and you'll see this. They're not random numbers, it's just I pick a number. And me as a data scientist, the number I like to use is 1, 2, 3 because I can remember it, and I always say start with 1, 2, 3. So my weights always start 1, 2, 3, and my bias always starts 1, 2, 3. And when I run this measurement through, it comes out and it says 0.3, 0.4, and 0.3. So what does that mean? It says based on these and the little bit of data I might have already seen, or in this case, haven't seen at all, I'm 40% sure that it's a type 2. Okay, or I'm sorry, a type 1. So remember, this is type 0, this is type 1, this is type 2. So it's mostly thinking it's a type 1, but notice it's not real convinced. It's only 40% versus 30% sure. So I wouldn't say that's a real great prediction. But again, this is a neural network, also known as a perceptron, when it's single layer like this. Okay, so now what we got to do is we need to get this algorithm to be a little more confident of its prediction than 40%. Okay, so writing that out as a vector again, it looks like that. That vector is there. Okay, once we have that vector there, let me get this off the screen because that's a little confusing. We do some more steps here. Okay, so what we want to do is we want to know, not 40%, 30%, 30%. We want to know which one it is. So we kind of use that squashing function and we say, in fact, we think this is a 1.0. It's that one. Okay, but we have to apply something called a loss function. And you'll see where this comes into play next. The loss function says, how close am I to the actual prediction? And how can I get closer? So what this is showing here, okay, is this is the actual prediction. So that's the actual prediction, and this is what that is the actual value. This is the predicted value. Okay, what we want to this number closer to that number. Okay, so this is the labeled data and this is the answer. So how do we do that? We use something called a loss function in math, and it works like this. We say, what is the difference if I subtract each of the individual probabilities? So what's the difference between these two? 0.3. What's the difference between these two? 0.6. What's the difference between these two? 0.3, right? Then we're going to sum them up and square them, essentially. So if we sum them up and square them, oops, I went a little fast there. I'm really good with math and talking here, but essentially our loss is 0.16 if you do the math on there. So our loss is 0.16. What we need to do is get that loss down. So the math, if you look at this, is really kind of simple. It's not that hard. But what we need to do is get the loss better. If we can get that loss down, essentially the predicted probabilities up here should get better. So let's talk about this loss function. There's lots of different loss functions you can use mathematically. We'll just take a look at some simple ones. So these are the weights. Specifically, what I'm going to do is graph out here the weight for feature 1 coming in. And the loss is, if you remember, we squash it with a sigmoid function, and it always has to be between 0 and 1. And if you remembered, our last one was 0.16. Okay, and what we want to do over time is that's obviously not 0.16, but well, it kind of is there. But what we're trying to do here over time is we need to get the loss function down as far as we can. When the loss function goes down, the accuracy gets better, is the theory. And what you'll see in the real world when you do these algorithms is you'll see the loss function starts out really high. right? And then just like this says, it drops off quickly as it learns, right? And then what it does is it starts to level off here. And then sometimes what you'll see is that you'll have, and I kind of have that up here, it'll jump up for a little bit and then it'll level back off. And what it's doing here is it's exploring. So it's saying, hey, should I go and take a different path to my learning? And then it quickly says, nope, I wasn't right. And I come back and then it starts to again level off. So that's what we want it to do. All right. We want it to get closer to 0. Okay, and we're going to do that over every training iteration. So this is training iteration 1, 2, and 3. So every time we see that data and we train on it, we want to get the loss function down. But how do we get the loss function down? Okay, let me take a quick sidebar here. What I showed you on that last one is if we're just looking at a two-dimensional loss function. So what I mean by that is I just have a single variable, a single independent variable going into my formula. But usually when you deal with pictures, it's you have like 3 dimensions, which is the red, green, and the blue, if you want to think of it that way. So the loss function kind of sits on a plane. So my loss function is there, right? And I need to basically say, I want my plane to go more down than up, right? And specifically, I want it to go down as far as possible. So this is kind of hard to visualize, but again, we need the loss to get closer to 0. And it's depending on how many features we have, this plane gets kind of out of shape quickly, but we're always trying to move it down is the key thing. All right, so let's go back to this real quick. Here's the numbers coming into the neural network, and there's the answer. Again, it thinks 0.3, 0.4, 0.3. The actual is this one. We need to get these numbers higher, specifically that number. So how do we do that? Okay. All right, once we run through this the first time, we get a loss function and we need to move it down. So the way we move it down so it doesn't lose as much, so the loss function gets lower, is we adjust the weights and the biases, right? Okay, so the weights, the bias is just the system variable, and the algorithms adjust that on their own. The weight is what we want to do is adjust the weight such that the loss function goes down. And you can do this mathematically, right? But what we're doing is adjusting the weight. So remember, I always start out with weight of 1, 2, 3 and bias of 1, 2, 3. Mathematically, it figures out what the new weight should be after it's seen many of these. Okay, so after it's seen maybe 10,000 of these calculation or these measurements, right? It's going to go and say, hey, I'm ready to adjust my weights and my bias, and then it tries again. So let's see what that looks like. Okay, what we're going to do once we adjust, once we get a loss function out the first time, okay, then we're going to adjust the weights and biases, and then we're going to do something called back propagation. And what we're going to do is say, train it again. Go through all of the data and process it through the system, right? And when we process it through the system, the only thing we're going to change is the weights and the biases based on our loss function, right? That's called back propagation. So what we're doing is we're saying every time we send these measurements through, batches of them, we're going to get a new weight and a new bias, and we're going to that new weight and new bias is an output of the loss function, and then we're going to send it back through the system. That's back propagation, and see if we can get it better. All right, so what happens? Now we get it through, and let's say maybe I went through there a little bit quickly here. Let me get rid of some of this garbage here. But basically, the first time we went through, we were at 0.3, 0.4, and 0.3. Now we back propagate. The new set of measurements, because we've adjusted the weights and biases, is this. All right, notice this is getting closer. This is a good thing, okay? But it's still only 70% sure if of its prediction. All right, so what's the loss function this time? So do the math. The difference between these is 0.2. Here's the difference is 0.3, and here the difference is 0.1, okay? I sum all of these up, so that's 6, and I square that. And I've got 0.04. So my loss function went from 0.16 to 0.04. It's going in the right direction, but we can do better. So what do? Based on the 0.04, we adjust the weights, we adjust the biases, and we do it again. And we're hoping the next time through, we get even better numbers. And we want those numbers to look very close to, perfection. That would be the goal. So that's training. This goes through rather quickly. Each time we train, we're going to get a series of new results through the back propagation, right? And we're going to calculate the loss function after each time, and we're going to put it back through, and we want it to get better. Right. So here's an example. Okay, once it gets better, we're going to validate it on data where we're not going to give it the answer, and we're going to see if it can figure out what the answers should be. So here I go through. My actual is this one, right? And it's very close. It's 90% accurate, or it's 90% basically probabilistically that it's a case 2. So case 0, 1, and 2. So it's working. So we're going to validate it, and we know that's right. That's how it works. So it works something like this. Okay, you've got all these features going in. Okay, and these are the features. So if you remember, this would be maybe the first example. This is the second example. This is the third example. And remember, these are the measurements, right? And then we're going to multiply that by the weights that we've determined and the bias we're going to add in. Okay, what you're doing here is something in math called matrix math. So it's very simple. And if you do this on a CPU, and you do it over and over and over again, CPUs tend to be a little bit slow on matrix math, which is why you use something called a GPU when you do deep learning. And a GPU is basically an NVIDIA graphic card. NVIDIA and just GPUs in general can do matrix math very, very quickly. So that's why you hear people saying, oh, you need GPUs to do deep learning. Well, if you're just doing a couple of these calculations, you don't. But when you're doing them over large amounts of data, it helps. But basically, this is the math that it's doing. So it's matrix math. It's the actual feature inputs times the weights and then add in the biases. And then each time I'm going to learn and get better with this. All right, so that is, however, looking at this data, data that is lengths and widths of sepals and petals. But we want to look at images, right? Who cares about 4 numbers? I want to look at images. Well, it turns out that you can do the same math tricks using image data. Okay, so here's a picture of an iris, and we need to figure out if it's a class 0, 1, or 2. Here's generally how you do that. All right, so what you do is there's many different techniques, and I'll just take you over a few of them. And then again, if you want, download that Git repo, and you can do this on your own, and you can figure out all the different techniques, and there's tons of them that mathematicians use to do this stuff. But here's one technique. What this is doing is we overlay a grid over the image, and what we're doing is we're saying the pixel intensity we're going to give a number to. Okay, you know, basically a 0 is not very intense pixel. You know, a 2 is more intense and a 3 is very intense. Those are just made up numbers. It's not actually what the image does, but just kind of follow along here. So that's one way to do it, is pixel intensity. Here's another way to do it. You do it pixel intensity based on the color, which is the channel. This is how most people do it. So there's 3 channels there, the R, G, and the B channel, right? And I'm going to give numbers to each of those. And then what I'm going to do is split those out. And then for every R, G, and B value, I'm going to run it through the neural network. So what would that look like? Okay, well, again, I have RGB. I'm going to run it through a neural network, and I'm going to adjust the weights and the biases. And then after I see so many images that are labeled so that I know if the answer is right or wrong, I should be able to learn and back propagate through this. So that's the theory. Okay. How does the math work when I'm going through here? All right, so here's another one. Basically, we create what's called a feature map here. And this feature map, again, this is the pixel intensity thing. So around the edges, you know, I don't really care too much about that. I'm not cared about the, you know, the pixel intensity. So I give those as a 0. You notice I get a bunch of 2s and a bunch of 3s there. Now I can play math games with this. Let's assume it's just a black and white image, so we don't have to worry about the RGB channel. And we just want to do pixel intensity here of a black and white image. Okay, what you do, here's one technique. You can create what's called a filter. A filter is always smaller than the data you're looking at. So this is a filter, okay? And this is called, and what I do here in the filter is I say the filter, I'm going to give random numbers to start with. So you can kind of think of these as the weights, okay? So those are the weights I'm using, right? And as we back propagate, we'll change those numbers in the filter. This is called, these filters, this particular filter, the way it's written here, you'll hear this data scientist talk about what's the kernel size. This is a kernel of 3, which means the filter is 3 by 3. So 3 down and 3 across, right? So that's a kernel of size 3. And what we're going to do is do a feature map. So here's one way to do the filtering. So we overlay the filter on this and we do simple multiplication. We multiply this number times this number. this number times this number, this one times this one. Oops, I can't write anymore. My pen must have died. But you get the idea. And what we're going to do then is output a single number coming out of it. So it should be pretty obvious what these are because there's a lot of zeros here. Basically, you have this is, yeah, again, my pen died. You notice the 3 times 1 is 3 and the 2 times 1 is 2. The rest are all zeros, right? And we get an output out of that. And I think my machine totally locked up.
We can still hear you, but looks like, yeah. Hello, Dave, is still there? Looks like we lost him. What about other people? Can you still hear me? You can just type in the chat window.
We can hear you.
Okay. All right. So let's give Dave a couple of minutes so he can join us again.
Hey, this is Dave. My machine died. Sorry about that. Are you?
No. I think we can. So, are you logged in from your cell phone now?
No, I'm on another machine. But unfortunately, I only have that presentation on that machine. So, does anybody have any questions while I try and get that thing rebooted?
There is a question in the chat window.
Sure.
And regarding your presentation, and sorry for
Sure.
the background noise. My son is with me.
Oh, that's
Did you
okay.
happen to upload that to that OneDrive folder link we shared with you?
I didn't. It's in the GitHub repo. Or
Oh,
it's in
okay.
the Git repo I mentioned.
Okay. So the question we have is, how do we determine the next set of weights and bias?
So again, the machine does that for you. So when it does back propagation, it will figure out what the next set is. So that's why I start with something kind of random, like 1, 2, 3. Something it's not again random. It's just a starting point, a jumping off point. And then basically what I do from there is I have the algorithm say that's why the loss is always so bad on that graph the first run or two through, because I started with basically something that's nonsense. And then what the algorithm does is says based on the loss function, adjust that number, adjust the weights and the biases down so that the loss function gets better essentially. Does that make sense? Are you guys there?
Yeah, we
Hello?
can hear you. And I
Oh,
think looks like Ajay responded. That's yes. Looks like the answer you gave makes sense. So Dave,
okay.
since we have 18 minutes left and you mentioned a lot of stuff is in the GitHub, is it possible for you just quickly share, like open GitHub and then just walk us through what are some of the resources are there so we can, so that will be really helpful for the attendees.
Yeah, sure. I'm actually just about have my machine back up. So,
Okay.
yeah, just give me 1 second. Uh,
Okay.
Sorry about that. These things
No
always
worries.
happen at the
Yep.
worst time, right?
Yep.
Just give me 1 more second here. No other questions?
Yep. No other questions so far.
Okay. All right, I think I'm back on. Can you guys hear me? Hello?
Yes, we can hear you.
Yes,
Okay.
yes, we can hear you fine.
All right, so I'm back up again. And let me put this back up on the screen. And all right. All right, so hopefully you can see this now. So I'm not sure exactly where I died, but we build a filter and then we do some math on it. So we place the filter over top of the image and we do multiplication of cell by cell. So there's a lot of zeros there. The math is easy. It's 3 times 1 is 3 and 2 times 1 is 2. So it gets 5 out of that. Okay. And then what we do is we essentially say put the 5 in the middle square. So if that makes sense, what we did there, we take the 3 by 3 or the kernel 3 filter, we place it over the image. We do math, we multiply cell by cell, and then we take the result of that and we put it kind of in the center square there, right? So 3 times 1 and 2 times 1, add those together is 5, right? Then what we do is we move the filter 1 over. Actually, you can move it over as many as you want, but we usually start with 1. And then we do the same thing again. We do the multiplication of the 3 by 3, and then we add up the results of that and we put that over here. So I'm not going to add that up all for you, but you can see that and we get some numbers. And we keep doing that until we slide through the whole thing, and that's called that process is called convolving. So that's where a convolutional neural network gets its name, because primarily the trick we're using is convolving over the data. And what we get is we get something that looks like what's on the right-hand side. And what this is doing is exaggerating the pixel intensities, or it's exaggerating the features. It's keeping the most important data and it's removing the rest. Okay, so that's convolving. But there's lots of other tricks here. So here's another trick here. We call this the max. I'll put it up here in a second, but basically we start this way and we say take a 3 by 3 kernel, and this time we just say give me the max. So this is what's called pooling. We say take the max value and just write that over here. What we're attempting to do here when we go through this is downsampling or pooling, but we're doing the same convolving process. Is what we're doing here is we're saying I want to get a smaller set of features than what I started with. So if you kind of take a look at that, my image is big on the left and it's smaller in the right. And again, it's much more intense. I've really exaggerated those features. So this is a trick we use called pooling or downsampling. And you'll see this in the lab as well. So there we go. Here's what some of these tricks look like if I look at it from a pictures perspective. If I take a look at this one and I apply the filtering technique, I get something that looks like that bottom thing there, right? And what it's doing is saying pick out the most interesting features, right? So notice how it instantly got rid of all the background noise, and it's really just kind of honed in on the iris. It's pretty cool. Just by doing this filtering technique, it's learned that. This is the downsampling example. So this is what downsampling looks like. And again, it looks like it's not quite as good as the filtering technique, but you have these tools in your toolkit and you're trying to, again, get rid of the noise and give it something that the algorithm can look at, right? So again, here, these were, initially I went through, if you remember, I had the weights attached here, and then here's what the values ended up being. In deep learning, this is called feature extraction. So I extract the feature out of there. The features look something like this, right? And then I'm going to plug that in each of these levels here. So remember, this is the perceptron where I start and then I just go right to the end result. Each of these steps essentially builds more layers in this network. Okay, so I go from that original network that looks very small to something that's much more complicated. All right, so each one of these steps that I do adds additional layers in here, right? So you'll see these, when you look at pictures of a neural network, when it's described out on the internet, you have multiple layers based on each of these feature extraction techniques. And again, what I'm doing here is classification. So I'm trying to see which type of virus this is. Here it's 80%, through the system. Through its first training run, and then essentially it gets better, the more I adjust those weights and biases. So that's essentially, not sure what that's doing. That's essentially what a neural network does under the covers. In that GitHub repo, when you go out and you test this stuff on your own, essentially you can go out and you can kind of test these theories and you can kind of play around with them. And what you can do then, again, is you go out and you build one from scratch, and you'll see it's really hard to get good accuracies unless you know what you're doing. And it kind of gets a little frustrating. And then we go over and we show you how to do what's called transfer learning. So let me go back here. What you do essentially in transfer learning, let me swap this over real quick, because this is the really interesting part of this, because nobody honestly goes out and codes these things from scratch. So what you do is you go out on the internet and you find in GitHub or on various other websites, you find a neural network that does approximately what you want it to do. And then what you do is you steal that and you apply your problem to it. So let's say here, this is a very simple example that I have on the screen, but this is predicting whether or not it's iris of type 0, 1, or 2, right? But you don't want to predict irises. Let's say you want to predict whether or not there's a hot dog in the picture, right? So if you remember from a number of years ago, the am I a hot dog or not use case, you can do that simply by using a neural network that was trained for a different use case or on a different set of data. So I can train a neural network on iris data and then have it predict hot dogs. And people find that, like, really? You can do something like that? And you absolutely can. So remember, this is a very simplified example that I have here, but basically you're going to do some filtering. So that's going to put a layer in the middle here, and maybe you're going to do some downsampling, and that's going to put a layer here, and you're going to build up all of these layers, right? That's going to predict these irises, right? But the key thing is you have an input layer that has the raw image data, so that's this layer, and you have an output layer that gives your predictions. So it's prediction 0, 1, or 2, so the 3 different types. But all you really have to do, all the hard work was done in these middle layers where I've done all of this stuff. That's the hard work, right? All I need to do is change the last layer and say, instead of predicting irises, I want to do a 2 class, and I want to say basically like this, right? I want to say, am I a hot dog or am I not a hot dog, right? So this is the hot dog and that's the not a hot dog, right? So what you do is you say, take off this layer, right? And add the new layer and then train on my data. So instead of training on irises, train on pictures of hot dogs, and now go through the whole system again and retrain it, but basically say these layers in the middle, all of these layers, they're locked, and the only layer I want to train off of is my new layer, which is my end layer. That's called transfer learning. So again, I can take a neural network that was trained on irises, like I have here, and I can have it predict handwritten digits, because all I'm doing is saying all of the important stuff is learned at these layers, right? All of these layers is the important stuff. The last is just that final set of predictions. And that's as easy as it is. So what we do in that GitHub repo is we essentially say exactly that. Let me discard this. We say, basically take a neural network that you find on the internet, right? We want to look at it. It's this huge architecture, it's called. Once that architecture is out there, we say chop off the last layer and tell it to train on our data. Once it's trained on our data, now we've eliminated all of that coding work, and we've simply said, hey, we're going to steal somebody else's work and do it using our data sets. It works really well, and what you'll see in that GitHub repo is essentially you get almost instantly like 98 to 99% accuracy, depending on what you're doing. So we have a few minutes left. Does anybody have any questions? Again, sorry about the computer glitch there. It happens. No questions?
Yep. So far, so far, so we good. Deb.
Okay, so I put the information back up here. Again, if you want to go, it's a public Git repo. I don't have it on GitHub because when I created this is actually a couple of years old, but I've updated the code recently. But GitHub had some limitations on the size of the repos, so I have it in my private one. But it's still public. You can get to it. It's a lot of fun. It's something maybe you do over the holidays if you have some days off. Again, if you've never used Jupyter notebooks or you've never done Python coding, this is a great way to learn that stuff. And again, you don't have to be an expert in any of that. We walk through the concepts essentially. So again, we try building something from scratch. We find out, oh, it's a complete headache and a nightmare. And then we go out and we find something somebody else did, and we do the transfer learning trick, which is really cool. So I guess that's it if nobody else has any questions.
Thanks, Dave, for a really wonderful session. We do see there are a couple of questions just came in. So first question is from Ajay, and he's asking, so for transfer learning, we have to create our own data set and train model all over again.
Right. So you do not. You need to have your own data. So again, if you have a model, if you pull down a model that was trained to do the MNIST data, which is the handwriting stuff, so it predicts whether or not that's a 7 or this is an 8. That's a neural network that actually it generalizes really, really well, right? So then if you said, hey, I want to use that, and my real world use cases is I want to look at my manufacturing line, take a picture of products coming off the line, and I want to know if they are products that need to be reworked or if they're good quality products. So I'm looking for manufacturing defects essentially, right? The way you do that is you say again, I'm going to use the model that I got off of the internet that basically predicts the 7s and the 8s and the digits. And now what I'm going to do is I'm going to send in pictures of my manufacturing line, products coming off of the line, and I'm going to label them. And I'm going to say this set of data is good. These are good products coming off the line, pictures of good products. Then I'm going to have some with defects, right? And maybe I even want to classify. This is a classified as defect 1 versus defect 2 versus defect 3. And then what you're going to do is, again, you're going to take the neural network that you pull off of the internet. You're going to chop off the last layer, and you're going to say train it. Keep everything else locked. Don't change those numbers. Just change the last set of weights and bias, the last set of weights, not biases, and tell me if I have defects. And it's a very quick way to do that. So you do need your data, and it needs to be labeled. So you need to say these are good products and these are bad products. But you're not retraining the whole model over again. You're just training the last layer. So it's a lot faster. And then, again, data scientists, they love to do competitions on this stuff. So there's plenty of these that you can find out on the internet that you can do the transfer learning technique. And again, I show you in those labs, if you go and you do them, like how big these architectures are for these models. So I only showed you just the example, just a 2-layer architecture, but they have architectures out there for MNIST that's I think it's like 50 layers. But you'll see it out there. And then basically you just say, again, the last layer, just train off of that. So how is the question was, how is the image input labeled? So again, you send in images and then you send in a little text file. So the images is like, image 001.jpg, and then you send in a text file that says 001.jpg, and then like a number 2 if it's class 2. So that's how you do it. So you're sending in the metadata and the actual data. So that's how you do it. Let's see, was there any other question? I think that was the only question. How's the image input labeled? Yeah. So that's it. So this stuff it's a lot of fun to just learn how to do this stuff. So again, looking at it on your own, and then, you can build something again really quickly just by stealing other people's work on the internet, which is like I always tell people, I've been coding for a long time. And if they ever took away Google, GitHub, and Stack Overflow, I would be worth nothing because I just steal all my code off of those 3. But there you go. That's how this works. It's a lot of fun, and I hope you learned something, and I'll pass it over to the next presenter.
Yeah, thanks. Thanks, Dave. This was really, really nice presentation. I think attendees also loved